Hello, and welcome to my Lab 5 presentation, Applications of Faraday's Law. My name is Anand Jha. Let's begin. To introduce this lab and to state its main purpose, this lab asks us to apply Faraday's Law to falling magnets through non-ferrous aluminum tubes. It first asks us to experimentally calculate the time it takes for a magnet to fall through an aluminum tube, and then to model a magnet falling through an aluminum tube using Python and GlowScript. We will finally compare our experimental data to our computational model. Some fundamental principles that this lab goes over is Faraday and Lenz's law, which describe how a magnet falling through a non-ferrous tube will induce a current, and that current will induce a magnetic field that opposes the motion of the magnet. It will also talk about the Biot-Savart law, which describes the magnetic field generated by a dipole bar magnet, as well as Ohm's law, which states that the voltage equals the current times the resistance. This lab will also cover basic Physics 1 equations such as Newton's second law and the simple kinematic equations. So to cover our experimental data and measurements for this lab, the first couple lines of this slide describe the basic attributes of the magnet and aluminum foil, such as the dimensions of the magnet, the mass of the magnet, the length of our aluminum foil tube, and the width of the aluminum foil itself. The key takeaway from this slide is that the average time for the magnet to fall through our aluminum tube was about 0.48 seconds, where you can see on the right-hand side on the Excel sheet each trial and how long it took the magnet to fall through the tube for each of those trials. Moving on to our GlowScript model, before we jump into the model itself, let's analyze the code and some fundamental aspects of it. Two important aspects of the code are these two methods. The first method is to calculate the magnetic field of the magnet using Biot-Savart's law. This law is written on the right-hand side in equation form. On the left-hand side, we can see it's written out in code. And our second method is to calculate the magnetic flux through each ring in our aluminum tube, which uses Faraday's law. The equation is again written on the right-hand side while the code is on the left. Moving on through our GlowScript code, we have a while loop that runs as the magnet is falling through the aluminum foil to continuously calculate aspects of the magnet. The first aspect is that we calculate the magnetic force acting on the magnet, which, as we can see on the right-hand side, is equal to the induced current times the circumference times the magnetic field at the ring times sine theta, where sine theta equals the magnitude of the cross product between mu hat and b hat. Secondly, as the magnet falls through the aluminum foil, we continuously calculate its position and velocity using simple formulas such as F equals ma and kinematic equations. So here are the actual results from our model. We can see that once the model finishes, it leaves a blue ring at the bottom of our aluminum foil. We can also see that the model predicts that it will take about 0.561 seconds for the magnet to fall through the loop. And by looking at our velocity versus time graph, we see that the magnet has a decreasing negative acceleration as it falls down the tube, and that it eventually does reach a terminal velocity. So actually interpreting our simulation, one question that we have to ask ourselves is which color represents counterclockwise current and which color represents clockwise current? By using the right-hand rule, we can see that red represents counterclockwise current, as when the magnet is falling, red is apparent underneath the magnet, and because we know the magnet is falling north pole side first, we can determine that red is counterclockwise, and because blue is above the magnet, we can determine that blue is clockwise. Another question is what happens to the dynamics of the system when you flip the magnet around? If you flip the magnet around, the magnet would take the same amount of time to fall through the loop, but the colors would be flipped and blue would be on bottom. The third question was how does the total time and tube of the experimental system compare to the computational model, and how can we improve this accuracy? So we got a percent error about 14%. We could do better by getting a more accurate value for our magnet's magnetic moment, and we could also try to account for wind/aerodynamic forces acting on the magnet in the real world. Finally, what does the shape of the velocity versus time plot tell us about the forces acting on the magnet? Velocity versus time plot tells us that the magnet feels a force counteracting the constant gravitational force that eventually cancels the gravitational force out and gives us a zero net force and zero acceleration/constant velocity. So in conclusion, we determined that as a magnet falls down through a non-ferrous tube, regardless of which end of the magnet is dropped first, north or south, an induced magnetic field will apply an upwards acting force on the magnet that will make it approach a terminal velocity and take longer to travel through the tube compared to if it were just traveling through empty space. Some additional questions we can ask are, what if the resistivity of the conductor were reduced as close as possible to zero? If we decrease the resistivity by Ohm's law, the induced current would increase, and that would increase the the strength of the repulsive magnetic force on the magnet, making the magnet take longer to fall down our aluminum tube. The second question is, what if there were holes or slots cut into our aluminum foil? These holes and slots would decrease the surface area of the aluminum tube and therefore decrease the induced current and strength of the repulsive magnetic field, meaning that the magnet would actually fall faster through the tube. That is all for my presentation. Thank you so much.